没问题，就再有一个超长的就可以了。
Okay, so then let's resume. So Jiahua Tian will continue the part 2.
Yeah, so first thank the organizer for putting up this wonderful conference. And as Jie just asked me what's the meaning of this notation, it just indicates that our conference takes place at the union of last few days of January and first few days of February. So it's a super rigorous notation. So I'm giving the part 2 of this talk, and I promise you that the scope will be very different. So I don't want to bore you guys out. So this is the structure of the talk. So first, it's a super quick recap, and it will be super quick. And second is I'm talking about Mackay correspondence and some SCFT data, and I will explain why Mackay correspondence is important in this context. And third one is a very new brain box construction of the 3D equals 2 theories. So first, I promise it's super quick. So it's super quick as that. So I thank the organizers for scheduling me right after Ina's wonderful talk, so that I don't have to review the things that is covered like 20 minutes ago. So here the question is that are there any other ways to?
Cannot last 5 minutes. Please
yeah, my apologies. But anyways, I think the question is that are there any other ways to engineer 3D equals 2? Then yes, I mean from a geometric engineering point of view, we could use other constructions from geometry, or we could try to look for new ways, and I'll present the brainy ways that using the brain box construction. So first, let me just motivate a little bit that why we care about Mackay correspondence. The thing is that by Mackay correspondence, I'm actually talking about a class of geometry constructed by orbifolding Cn by subgroup of SUN, a finite subgroup of SUN. So this, of course, provides a rich class of varieties in geometric engineering, and in particular, they're all Calabi-Yau varieties, so they're good. And there's a very lovely feature of this kind of geometries, such that I mean in 2D, 3D, and 4D, in all those cases we do care about, we have a full classification of the finite subgroups of SUN. And in particular, they can be studied algebraically. And by that, I mean we could try to see that their conjugacy classes of the finite groups, they correspond to divisors of the result of the geometry. And the irreducible representations of the finite subgroup, they lead to intersection pairings of the geometry, in particular in 2D and 3D. In 4D, it remains unknown, that I will mention later. And also in many cases, we could simply just write down a hypersurface or complete intersection Calabi-Yau equations for those varieties, so that a lot of math and physics problem as statements can be concretely checked. So here's the familiar case where we study M theory on C2 over gamma, where gamma is a subgroup of SU2. And this is a very familiar case. And mathematically, we have the classification, the so-called ADE classification. We have the cyclic group, dihedral group, tetrahedral, octahedral, and icosahedral groups. So these are AD and E6, E7, E8. And for all these cases, we do have a Krapin resolution for those geometries. And we know that the conjugate classes of gamma, they correspond to the divisors, in particular the exceptional divisors of the geometry. And the irreducible representations we can simply write down a Mackay quiver and its adjacency matrix, and leads to the intersection pairing of the result of the C2 over gamma orbifold. And for all these cases, we can write down a hypersurface equation for those Calabi-Yau varieties, and in particular, I present a hypersurface equation for the AN type singularity. So now this is a less familiar case, and if you do feel so, you should just read my paper where it's nicely explained. So the physics now is M theory on a C3 orbifold, where gamma now is a finite subgroup of SU3. And in this case, we also have a classification 100 century ago by this nice guy. And for all these cases, it's also proved like 20 years ago that in all these cases, we do have at least one correct resolution of those geometries. And in these cases, the conjugacy classes are, again, they correspond to the divisors of the geometry, but then there's a question like what kind of divisors there, because in this case, we have this non-compact exceptional divisor and also the compact exceptional divisors. Also in this case, for the irreducible representations, we could also write down a sort of adjacency matrix, but in this case, it's an anti-symmetrized version of adjacency matrix, and it corresponds to the intersection pairing in the Calabi-Yau threefold. And in this case, we could also, for all these cases, we could either write down a hypersurface equation or a complete intersection equation. For example, in this case, if you look at Tn theory, and this will be the hypersurface equation of Tn embedded in the C4. So more on the 3D case. So sorry, by 3D case I mean Calabi-Yau threefold. So that's in field theory, that's actually a 5D field theory. So here, by conjugacy classes, by the relation between conjugacy classes and divisors, actually mean that first we define the H for a representative of a conjugacy class of the finite subgroup of SU4. And in this case, H ranges from 0 to 2. And there's a theorem proved by Ito and Reid saying that the 2 embedded number of the resolved Calabi-Yau threefold is equal to the cardinal number of gamma m. And there's another, and this theorem is translated in my paper with these nice guys to be a physical statement saying that the cardinal number of gamma 1 is equal to the number of exceptional prime divisors, while gamma 2 is equal to the number of compact divisors. So it will be gamma 2 will be the rank of the theory, while gamma 1 will be the gauge rank plus the flavor rank of the theory. So there's also the relation between the irreducible representations and the intersection pairing. So this one, the first definition is just a generalization of the Mackay correspondence in 2D. And the theorem says that you actually have an intersection pairing of the Grothendieck group of the resolved Calabi-Yau threefold given by that. So this is an anti-symmetrization of the adjacency matrix at level 1. And the physical meaning of the theorem is basically saying that the Smith normal form of the pairing between these two guys is actually equal to the Smith normal form of the anti-symmetrized adjacency matrix. So this will give you the one-form symmetry of the 5D SCFT. And this is just a pretty concrete example for that. So for example, now we look at Z5 given by this diagonal matrix action on Phi3. We can check the conjugacy classes. We have R is equal to 2 while the flavor rank is 0. And this is the Mackay quiver. We just write down as adjacency matrix and anti-symmetrize it. We'll see that we have a Z5 one-form symmetry here. And now the problem is that we want to construct a 3D n equals 2 theory, so that we have to make use of Calabi-Yau fourfold constructed by quotienting C4 by a finite subgroup of SU4. But in this case, we do have a classification by Hanani and He 20 years ago. It's a little bit complicated, but anyway, it's all classified. But then the big open problem is that for this Calabi-Yau fourfolds, we don't know whether there's a correct resolution or not when gamma is not abelian. So in this case, I mean, when gamma is abelian, of course, we know all these cases are toric, so we could just apply the toric criterion to see whether there is a correct resolution or not. But when gamma is not abelian, we don't have such means, so we don't know. But again, given that, assuming that there is a correct resolution, that we know that the conjugacy classes, again, they correspond to the divisors of the resolved Calabi-Yau fourfold. While the ERAPs do they do give rise to some matrix here, similar to the adjacency matrix in 2D and 3D. But at this stage, we are not sure like what the physical meaning of this matrix here. So
the last example, the last page, I don't understand why it's so defined.
Oh, this one I picked this one because this is toric. You could just write out a toric diagram.
Denominator is it 5 or
Typo to the typo, the 5. On the explanation. First row. First row?
Oh, sorry, that's 5. That should be 5. I'm sorry. Yeah.
okay.
Yeah, so let's go back to this 4D case, Kabial fourfold case. So there's a theorem by Joyce saying that if there is a Kraken resolution of fourfold x, then we have the 2k Benny number is equal to the Cardinal number of gamma k. And given that theorem and assuming the existence of a Kraken resolution, we could just simply say this is exactly the same as the 3D case. We could just say that gamma n minus 1 is equal to the gauge rank, while gamma 1 is equal to the gauge rank plus the flavor rank. So this provides some discrete data of the resulting 3D equals 2 SCFT given the existence of a Kraken resolution of the C4 orbifold. Again, we could define a matrix for the EREPs. So we could just define this AKL matrix, the A matrix at level n, and this will be the alternating sum of this different matrices at different levels. But then the problem is that we're still thinking about this, and this is again just an open problem. The thing is that what does A correspond to in the resolved Kabial fourfold? And the answer is that we currently don't know. But then we test that at least it does not correspond to the intersection pairing. So therefore, in this case, it does not give rise to any useful information about one-form symmetry of the 3D equals 2 theory. But then another question is that then what corresponds to the intersection pairing in 3D? And this thing is even not known for mathematicians. So we're still working on that, and probably just challenging you guys to give me an answer if you know.
Sorry,
Please.
Can you go back a bit? So what is this definition? So Q is the natural n-dimensional representation?
Yes.
But then you take n is the exterior power of Q.
Oh, sorry, that should be k. That should be k. So k ranges from 1 to n. And Q is always an n-dimensional representation.
So which representation?
So for example, if you're in Kabial fourfold, then that's a natural 4D representation of that.
Okay, that's
Yeah.
fine. And then what is rho k and rho?
Rho is different irreducible representations of that finite
You
subgroup.
consider all representations of.
Yes, yes, all the irreducible representations for that, and that can be checked. I mean, I mean, in most cases, these are, so for example, when this is abelian, then of course all the representation is just a 1D representation, but you can still write down define such matrices.
Okay, so then what is the exterior power? So is it still n's power, or as you mentioned, k's power?
Oh, you mean this?
No,
here?
the definition, right? So you're writing n's exterior power of Q.
Oh, that should be probably, yeah, that's a typo. That should be I power, I think. I ranges from
I
1 to,
power.
yeah. So for different i's, I define a different A matrix here.
Okay.
Yeah.
So then it should be A parentheses I also.
Yes. Yes. I'm sorry for the confusion. Yeah, it should be like changed O to I here. So there will be I and there's an I there. Yeah. So this is just a presentation of what we know, and this is a pretty ugly table. But anyways, it contains many useful information about the 3D equals 2 theory. Given, I mean, we assuming that the existence of a Kraken revolution here.
Sorry,
So-
this is country class of what? So this table.
Sorry. Okay. Oh, these are all from reading off the conjugacy class data of the finite subgroup of SU4. So for example, for all this conjugacy class, I can compute its age defined previously. So here, gamma 1, gamma 2, and gamma 3, they just mean that the number of conjugacy classes with age n.
Okay, so are these groups or country classes? So presumably all of these are subgroups.
These groups are just the labels or subgroup, finite subgroup of SU4, and these are the generators for that.
Okay.
So the generators are all defined in terms of SU4 matrices. Yes. So another thing is that, I mean, as I promised, that there are, I mean, you can write down hypersurface equation for some of the cases here. For example, I mean, here I write down a hypersurface equation for this F31st subgroup, and you see it's very complicated. And but this is at least an equation so that you could just try to see like what are the what are the singular locus of this hypersurface, and you can just do the weighted resolution for that and study all this intersection properties of the theory. But this is just computationally pretty hard, and we're just working on that. I'm just presenting this for you guys to give you a flavor that what we can do. And just a few comments before I move on to the next part. So whether a Kraken resolution is important, I mean that's actually a very good question if you do want to ask that. The thing is that in some paper we do study geometries with no Kraken resolution at all, but in the context of compact Labial, so that everything can be checked against the gravitational anomaly cancellation. So it actually makes sense. But in our case, the point is that we are studying non-compact Labial first. The second is that when there is no Kraken resolution, Joy theorem no longer holds. So we couldn't expect to have such a good match between the data of conjugacy classes of the finite subgroup and the ranks of the resulting theory. Another problem is that whether, since we don't know if the existence, if there's a Kraken resolution, we could study whether there's any meaningful deformation of the theory. Unfortunately, most singular loci are non-isolated, so we don't know a good theory of the we don't know a good deformation theory for this non-isolated singularities. And another problem is that whether there are finite structures there. So we could study, for example, in the context of Labial threefold, the triple intersections, or in the context of Labial fourfold, the quadruple intersections. But they cannot be read off Mackay correspondence. That's a short answer for that. Because Mackay correspondence is more like, I mean, encodes some topological data of the Labial fourfold. Well, I mean, this is triple or quadruple intersection, already stepped on the realm of geometry rather than just topology. And of course, I mean, you could study CY Labial fivefold. The problem is that we don't even know such a classification exists. Probably yes, but not that at all. So now it's I think it's the second part of the talk. So we'll study the brain box here. So if you're not worn out by all this math before, I promise that I'll provide more colorful pictures in this section before you go to the university canteen, which is not that attractive, I guess. So the punchline here is that the brain box is dual to a toric geometry. So here, as Yinan mentioned, that this will also be my primary example here in the second part of the talk. So this is again the P1 times P1, local P1 times P1 times P1 example. While here I have the brain box dual to that. You can see that this is simply that, I mean, whenever I have an edge here, I'm just having a plane dual to that. And I should say that this is actually more rigorously should be defined as the polytope corresponds to the toric fan of the Labial fourfold, and it is, if you really want to consider the full toric fan, then you have to put it on a W=1 plane there, and really draw the 4D fan there. So more precisely, I would say that the brain box is actually dual to the polytope corresponds to the toric fan of the Labial fourfold, which more probably encodes the local data of the geometry. So the thing is that the point that we do this brain box construction is because of course it's more we believe is somewhat more physical, so that you could simply if you want to study the degrees of freedom of the 3 equals 2 theory, you could just look at the brain movements in the box diagram, and because we don't really study the Higgs branch data of the theory, we just look at the, for example, the Coulomb branch parameters. Say the simplest case, in the simplest case, we study the rank of the Coulomb branch, or we could also study the extended Coulomb branch parameters. For example, the flavor ranks there, and also. We see that the dynamics of the 3D equals 2 theory that corresponds to some diagrammatic of the brain box, which I will explain in detail later. And also you could study the states, in particular those BPI states, before they're corrected in the IR by looking at the stringy or brainy states of the brain box. So it's just like in 5D where the stringy states stretched between the brain, the PQ5 brains becomes the BPI states of 5D field theory. Here you can have the BPI states coming from the stringy, or I would say later I'll present that also coming from D3 brains stretching between different brains. And also we could study the Halani beta moves of this brain box, which is nothing but a remnant of the familiar Halani beta move in the 5D case, actually. So here, I mean, again, here is just a warm-up case where I present a 7D geometry. I started from the Kaluza-Klein monopole in M theory, which I call KK7M. So this sharp just means that its Tn circle is along the 10th direction. So this is a configuration of a KK7M, and we know that this KK7M exactly is a toric CY4, toric CY2, and it's dual in 2A to parallel D6 along the 5 direction. Where you can see, for example, if I have two KK7M here, it's basically saying that I have a S1 coming from infinity, shrink in the middle, and again they just expand a little bit to be a topologically a sphere, and they shrink again and go to the infinity. So this actually is dual to a toric diagram here, where I draw this so that it's full toric diagram. But if you just care about the compact part, you could just erase this, so it becomes just a 2 edge connected by a point, where it is again it is further dual to 2 parallel D6 in this case. But in all these dual frames, we see that, I mean, either in the M theory frame, we see that there's M2 wrapping this topologically as 2, so that it's a double boson of the broken SU2 theory. And also in that case, we know that there's a 2A fundamental string stretching between these 2 D6. So now this is again a warm-up case where we focus on 5D. So here in 5D, I start with 2 KK7Ms with their Tn circle along 2 different directions, S9 and S10. So now this KK7M actually gives you a toric CY3, where upon the M theory 2B duality leads to a PQ fibrine web in 5-6 direction. So here I present a simple case where this is a local P2. So you can, so we could see that this local P2, this is actually sort of a moment map of the local P2. Where in the middle, in the chunk here, you have a T2 vibration over this triangle, the interior of the triangle. While on the edge, you have certain cycle of the T2 shrink. Different, and when you are at the vertices of this triangle, you will see that all this T2 shrink. So this whole thing gives you a P2. While this is just nothing but a local P2, where I also draw the whole toric fan here, because I mean I'm able to draw it on a 3D space, but not 4D. So here, this is just a familiar local P2. Well, of course, I mean, this local P tool, you can just apply the very familiar method to make it dual to a PQ5 brane web here. The upshot is that I mean, the PQ5 brane actually provides a bookkeeping method to see the moment map of the toric variety here. And in particular, I want to emphasize, I mean, this KK7M configuration is more, in some sense, just encodes the compact part of the geometry, where the non-compact direction, they stretch. So in this is easier to see. So the non-compact part is stretched until infinity of this 5-6 plane. So the lesson we learned from this warm-up cases in 7D and 5D are that, I mean, this toric geometry is nothing but like encoding the information of various degenerations of the TN fiber over some configuration of over Rn. So for example, the CP1, we know that this is nothing but a S1 fiber over a interval such that it shrinks at the two ends of the interval, so that is topologically a sphere. While in the CP2 case, as I've already said, I mean, you have a T2 fibering over a triangle where this T2 shrinks over the edges and the vertices here. And KK7M configuration exactly encodes such information of this shrinking S1s in the geometry. And we get a brane configuration via M theory and type 2 duality. As in 7D, we get this brane configuration via this type M theory and type 2A duality, whereas in 5D, we get this brane configuration via this M theory and type 2B duality. And the important takeaway message is that the edge of a toric diagram is actually dual to a plane or a brane in the brane diagram. So the thing is, the important thing is that we know that we could, for example, in this diagram, we know that we could just draw this picture as a bookkeeping device to remember this moment map of the toric variety. But without using the M theory or, I mean, the string dualities, there's nothing you can say about whether there's any dynamics to that configuration. Because at this stage, if you don't use any string duality, this is just nothing but a set of intersecting edges here. Until you actually, I mean, apply the string dualities, you know that these edges actually, they are dynamical branes in string theory, which is actually important because in the 4D case, we'll try to target what are the dynamical objects there. So this is the main case of our consideration, where we're now dealing with 3 different KK7Ms. Now you can see that this TN circle along different directions, and you also see that there is a perfect SL3Z symmetry that is manifest in this construction. So you can see, I mean, for example, you can have this SL3Z swapping in the 5, 6, 7 direction, or swapping the the TN circles here. And this KK7M, in the simplest case, you could just draw a tetrahedron case, where this actually corresponds to a local P3. And you can see, I mean, in the bulk of this tetrahedron, you have a T3 fibration over it. While on the faces here, the T3 fibration shrinks to a T2 fibration, and of course on the edges shrinks to an S1, while on the vertices shrinks to a point. So all in all, this gives you the moment map of a P3. While on the other side, you can see that you just draw the dual diagram of this P3 of this moment map representation of T3. You can see that this actually gives you an intersecting plane configuration. But as I have emphasized like 2 minutes ago, so this intersecting plane configuration, for now, I didn't say what are those guys in string theory. For now, it's just another representation of the toric diagram here. And now, here comes the question as I emphasized, like what are those planes here? So in 7D, we know those edges, there are the D6 branes, while in 5D, we know those edges are the PQ5 branes. While in this case, we first, so given this KK7M configuration, we first do an S1 reduction on this S10. So here you see, I mean, in 2A, so first we go from M theory to 2A, where this KK7M becomes a D6, while this KK7M becomes a KK6, this 2 KK7M becomes KK6A, the KK monopole in type 2A. And then we'll do a T dual along this direction. And this gives us a intersecting brane configuration D5, NS5, and KK6B on T2. Because now we have two S1s here. We have two S1s here, S1 8 and S1 9. This is the T dual direction, while this is the original M theory direction, where you have a Tn circle of the last KK7M here. So now we arrive at a 2B configuration with D5, NS5, and KK6B. But now you could already see that this actually resembles the structure of a 5-brane web, because I mean these are nothing but the basic building blocks of 5-brane web. But now we have another direction. So imagine it's just that we have a 5-brane web, and along the other direction we have a KK6B. So it's like we have a but the good thing is that in this case we could go to the physical or the mathematical limit where the KK6B basically decouples, and we could check many statements against the 5D case by decoupling the extra KK6B, and we're arriving back at a configuration of PQ 5-brane web. So now we see that these planes or branes can be labeled by its normal direction in 5, 6, 7. So for example, in this configuration, I label D5 by 100 by 100. So it's normal to the 5 direction because it's occupying the 6 and 7 direction here. And also, I can study the BPI state stretch between the different branes here. And this F1 and D1 strings are nothing but the familiar things in the 5D brane web case. While this D3 is adding a new new ingredient to the theory, where you can see that this actually carries, because these strings or branes are labeled by the 4 branes here, by the type 2B branes here that they can end on. So this D3 branes, you can see that it is, because it's along the 7th direction, so it could end on the KK6B here, which is labeled by the normal direction. So this is just a notation here. The new ingredients here is the extra D3 brane, which plays the role of a 001 string in 3D. So now,
I still don't understand how these arises from this geometry, or like the same from. So I understand the meaning of D5 and S5 KK6B.
yes?
But where does D3 come from, or you just add it by hand?
Oh, actually, okay, I think I skipped some steps. So actually the thing is that the original KK7M, you can study the M2 branes wrapping various cycles in the geometry. So cause that's a geometry. So this F1, D1, and D3, they are nothing but the dual objects of this M2 branes in the original geometry.
Okay.
Yeah. So I skipped a step. But everything can be studied in the KK7M configuration. And then you just via different string dualities, not only the KK7Ms are dual to D5NS5 and KK6B, but also the BPI states given by the M2 brane wrapping modes, they are dual to different states in other string frame. Yeah, so these are from the M2 branes, actually. So here comes the puzzle. So where's the SL3Z symmetry here? Because before, I mean, in this configuration, okay, I'll just use my laptop. So you could see in this configuration, in this KK7M configuration, there's actually an SL3Z symmetry here in the 5, 6, 7 direction and also in this T3 direction. But here in 2B, we see that we actually lose that SL3Z symmetry, at least a manifest SL3Z symmetry. So now here comes a rescue, so that because as I emphasize, this geometry is actually 2B on a T2, where you have this SA and T dual S9 direction. So let's look at the 10D algebra actually. This is a 10D algebra on R1 7 times T2, where you get these two terms here. And now you just do a reduction on T2, you get this AD algebra. But now you find, I mean, there's a perfect SL3Z symmetry here given by the central charges. They're not really central charges because they're carrying some space-time indices. But you can see that there are these charges carrying this PQR label, and they are perfectly symmetric among themselves. And you have this SL3Z central charge Z arising from this reduction of the 10D type 2B algebra. So now, if you just work in the AD maximal supersymmetric theory, we see that the PQR labels are totally symmetric in AD, where we recover this SL3Z symmetry. And from now on, we just call them the 4 branes. And we have this PQR 4 branes on these different directions. And if you just look at here in the 5, 6, 7 direction, you will see that this actually becomes a box diagram, because you have this 1004 brane that is normal to the 5 direction, and and all the general PQR branes normal to the PQR directions. And you also have these strings coming from F1, D1, and D3. And that's the reason that why I label those different fundamental objects in 2B by a PQR charge, because in AD, when you do the T2 reduction, it actually becomes something that is charged under the central charge that I just present in the AD superalgebra. So now there are also some features of this brane box diagram. So for example, the first one is that there's a static condition for the branes, and in particular for this branes to be like stable in a stable configuration, I have to require that the tension, the sum of the tension of the branes at the intersection sum to 0. And it's a nice feature about this expression for the tension of the branes that they are linear in P, Q, and R. So this summation equals 0 translates into the sum of P is equal to the sum of Q is equal to the sum of R is equal to 0. So that's a static condition for the branes. And it also translates via different dualities, or by just looking at the tension formula of the strings themselves in AD, that there's a charge conservation for strings as well. And it also says that the sum of the P charge, Q charge, and R charge is equal to 0 at the intersection of various branes. Various strings. So one should also compare all this stuff to the 5 brane web case, where you also have this charge conservation condition and also the static constraints for the PQ branes. And in particular, if you combining the static condition and charge conservation, we know there's also a brane bending in the brane box case, where if you have, for example, in this case, if you have a 0, 0, 1, 0 brane going at a 0, 0, 1 brane, it will bend the 0, 0, 1 brane to 0, 1, 1, so that you can see along this edge of intersection, it satisfies the first static condition here. So this is an important thing coming from just looking at the tension of the brakes. So now I have a pretty good dictionary between the PQR4 brane box and the toric CY4 construction that is also mentioned by in Yan's talk. So now I have a brane box, and we know, as I emphasized like 10 minutes ago, so the brane box is actually giving a moment map of the toric CY4, or more precisely, gives you the dual of the polytope corresponding to the toric fan of the CY4. And a PQR4 branes in the toric CY4 geometry is nothing but the locus of a degenerating PQR cycle of T3. And I'll explain that a finite cell is actually corresponds to a compact divisor of a Clapeyron fourfold, while a semi-infinite cell corresponds to a non-compact divisor. And here you will also see this. There are this not only the semi-infinite cell, but you also have the semi-infinite 4 branes coming to infinity. And these are nothing but the normal direction to the compact divisor it intersects at. And also there's a charge conservation, which translates to the Clapeyron condition of the toric CY4, of the toric geometry actually. So that the last line here probably, in the last page probably needs more explanation. So here, the Clapeyron condition actually means that for any compact divisor here, you have the normal bundle to this compact divisor is equal to the canonical bundle of this compact divisor everywhere. So you can, for example, just consider this compact divisor here and look at this edge. And this actually means that the Tn action, because that's a toric geometry, so there's a natural Tn action. So the Tn action along this edge must match on the two sides. So that will actually tell you that, because the Tn action is given by the PQR charge. So that actually tells you that the PQR charge should match between the two sides, which translates to the charge conservation condition. So there's a bonus after I hear Junior Yagi's opening talk of this conference. So this is an M5 brane configuration that is dual to our KK7M configuration, which is quite similar to his setup in his construction with the T3 directions and the R3 directions swept. So I believe he has S1 there and RRR there, but we have this direction swept. So I'm not sure like whether there's a deep relation between these two configurations. But in any case, this is an M5 brane configuration, which could be useful in other contexts. So now let's test the Coulomb branch physics of our brane box construction. So first, of course, we want to match the discrete data of the Coulomb branch, and here comes the first obvious test is the rank of the Coulomb branch, and we claim that the rank of the Coulomb branch is equal to the number of local deformations of the brane box. So by local deformation, I mean that we should fix things that are global, and in this context, the global stubs are the branes that stretch to infinity. So we fix this guys, and this central finite cell is kind of breathing. So that's a local deformation of such a brane box. And for this, we could just count that each PQR4 brane, the finite PQR4 brane, they provide a 1 degree of freedom of the local deformation along its normal direction, while each edge is just a one constraint there. And the vertex, each vertex is one redundant constraint. And there's a connectivity condition because we're considering one big brane box. So that provides one constraint. So that means the rank of coulomb branch is equal to F minus E plus V minus 1, which is pretty ugly. But here we just summoned the power of mighty Euler. Because the whole brane box can be viewed as a polygonization of S2. Sorry, R3. So we have this Euler formula for this whole thing, and we finally arrive at the expression that rank of the coulomb branch is the number of finite cells in the brane box, and this also match our result in the toric geometry language. So this passed that test, which is nice. So also for this counting issue, you can just say that I have this brane box here, and because I just said this is a rank 2 theory because there are 2 finite boxes in this brane box, and this, as I said, you always have a KK6B direction that you can decouple or so that it recovers effective brane web. So in this would mean that you sort of either you squeeze or you stretch this side to infinity, this direction to infinity, and you will arrive at this PQ5 brane web, which was mentioned in the talk. So this could provide a test case for the brane box construction in certain limit, I believe. So we could also test the U1 coupling in the UV here. So here this is in the UV because I want to write on Lagrangian, and only in that case I have a control of the theory. So for this Lagrangian, we could see that the gauge coupling here is 1 over G squared. Is exactly the same coefficient in front of this the kinetic term of the real scalar field phi. And just as said, this local deformation or the kinetic energy is actually corresponds to sort of the breathing of the whole finite cell. So of course it involves the movements of all the branes that are facets of the finite cell. So now you will see that the kinetic energy is nothing but this is just a primary school level knowledge that you have the kinetic energy is equal to 1/2 times m times v squared, and this gives you sort of the velocity, and the mass of course is proportional to the area of the brane of the forebrane bounding the finite cell. So you will see so that we finally arrive at the expression that 1 over G squared is equal to the sum of this expression. So now I'm expanding the dictionary that I presented a little bit earlier. So you have the brane box is moment map, while the finite cells are compact divisors. And now the finite facets are nothing but the divisor of this compact divisor. So each AI is actually the area of each finite facet is actually the volume of such a divisor in the compact divisor. So this then translates to this sum then translates to the sum of all the divisors in the compact divisor D, which is nothing but the volume of the anti-canonical bundle of D. So that also match what we have in the toric construction, at least in the realm when the perturbative description, when the Lagrangian description can be trusted. So now we could also study the states in the brane box, where the mass, of course, is the mass of a particle. If it is coming from a string stretching between the branes, then of course the mass of particle will be equal to the mass of the strings, which in turn is proportional to the length of the strings. And the charge, we propose a equation that is quite that is analogous to the equation in the Aharoni-Hanani-Koh paper, where the electric charge of a string state is equal to minus the number of finite branes it ends on. So now we could also check different enhancement limits of the theory. So for example, if we want to look at the non-abelian enhancements of the theory, we could just let the mass of the W boson goes to 0 so that we have U1 enhanced to SU2. And in this case, we choose, because this is an SL3Z symmetric configuration, so now we just choose the strings between these two guys as our W boson, so we just shrink it, and until we get this configuration, where here it becomes just nothing but, because this is a fibro direction, so when you shrink that, it becomes just the volume of the base. And this will give you the bare coupling of the enhanced gauge theory in the UV. So for the flavor symmetry, we actually need more structures. So for example, in PQ 5 brane web, to study the flavor symmetries, we add 7 branes that the 5 brane can end on. But now in this case, we have to, because this solid lines are the branes in the brane box, while the dashed lines are the things that I add. So the question is that what are those dashed lines so that the semi-infinite 4 branes can end on? So there are several requirements. The first thing is that if we add more branes into the configuration, the whole thing has to be supersymmetric. And also the 4 branes can end on them translates back to the M theory configuration. That would mean that you will have KK7M can end on other objects as well. So, and also because we are considering the BPS states, which are either the strings or D3 branes, so that we must have the strings or D3 branes can end on them, which translates back to M theory configuration. That will mean M2 branes can end on them. And they should also carry certain charges in AD superalgebra, because we want them to be AD, the dynamical objects in AD. And we also expect them to have some SL3Z properties, because I mean this is the symmetry property of the whole configuration, and you don't want to break that. This is just a U-duality of the theory. And here comes the Deus Ex Machina solution. And yes, there are indeed these 5 branes in AD, and these are in particular codimension 2 in AD, which resemble the property of 7 branes in 10D. So these are all the codimension 2 branes, so that we could, for example, in AD, we could also study this branch cut and the other things, just like we study the 7 branes in 10D. So now these are the SUSY configuration here. So these are all the things that I can add to the original KK7M configuration without further breaking supersymmetry. And now I'll just first do a reduction on S10, where the different KK7Ms giving rise to different objects in type 2A, while a further T-dual on S9 gives you this guys in type 2B, where I mean D7, NS7, and D5, NS5 are pretty familiar objects to us, while we also have these 2 kinds of branes called 522 and 523. These are the so-called exotic branes in type 2B, and was studied in this paper, if you're interested. So the first requirement is that they are compatible, aka supersymmetric, and this is checked. And also, their charges can be read off the TN configuration, the top knot configuration. So the result is that we have this 1005 brane is nothing but the T2 rep D7 or D5, and we also have this 1015 brane and 0015 brane. They coming from different sources of the T2 rep thing, or the 2B thing without and with no T2 reduction. So it actually, the charges here actually determines which 4 branes can end on them. So, but then the question is that why there are 2 of them. So this is some kindergarten math. So it's like, so now I have a 4 brane 100. So of course it has essentially 2 directions it can end on. So it's either the 010 direction or 001 direction. So here comes the rescue. Rescue is that we have for each of this PQR branes, we have a pair of branes that it can end on that reflects the fact that we are in 3D, not in 2D. So it's not only just one direction it can end on. It can end on the linear combination of two directions here. So now in a brane box system, we have the facet here. Each facet is a 4 brane, while each edge at infinity is a 5 brane. And now this is nothing but a choice now, because we have the freedom to choose like which branes are which ones that the 4 brane can end on. But this is just some notation here. So and the 4 branes can end on them means the KK7M can end on them as well, and it's also checked where the string duality is. So now we also have to check whether strings and branes and D3 branes can end on them. So you can find this configuration where this F1 and D1 can end on this D7, D5, or NS7, NS5, which is a familiar result in type 2B, while you have this new result there that such a wrapped D3 can end on this exotic branes, which is less known before. But this actually reassures that a PQR string can end on a PQR 5 brane. Because we check, I mean, these are nothing but this F1, D1, D3 are nothing but 1, 0, 0, 0, 1, 0, 1, 0, 0, 1 strings, and they end on the correct, the 5 branes with correct charges. And for the other two requirements, you can just check a paper from 2 decades ago, where they do carry certain charges in 8D superalgebra, and they also satisfy certain SL3Z transformation property. And also there's a Hanani-Witten move, because that's a 5D Hanani-Witten move, where you just turn the direction of the branch cut, so it bends the brane, and then you just stretch it across the brane and to realize the Hanani-Witten move. That's a brane. So you just create a brane here. So it is the same thing happens in our brane box system, where you can have a 5 brane here. It's a codimension 2 brane in our system, and you have a 4 brane here. So now you can generate a branch cut in this direction, so that it bends the brane, and when you move it across the brane, it triggers a brane creation process. So here are some comments of the construction. The first thing is that the U duality, the SL3Z symmetry, is manifested either in the KK7M configuration or in the 8D superalgebra, and also there are many things that resemble the case in fibrate web. So you can check many systems against the known 5D cases. But this is also very much more complicated, due to the existence of various exotic branes where we know a little about their brane dynamics. So now we could also study, after adding those stuff, I could also study the flavor rank of the theory, and I claim that the flavor rank of the theory is equal to the number of global deformations of the geometry. So by global deformation, I mean that I have to fix all the external edges so that I can only have a dynamical process of the finite guys. In this case, each semi-finite, semi-infinite 4 brane provides a 1 degree of freedom, and there are 3 overall translations, XYZ translations, that are redundant. But each external edge provides 1 constraint, but 1 edge constraint is redundant. For example, if you imagine you shrink it down to here, so after you fix all the other 7 edges, the 8th edge is already fixed, so it's a redundancy. So this will give us that the rank of the flavor symmetry is equal to fx minus ex minus 2, where this f and ex means just the number of external facets and external edges. So again, this was pretty ugly. So you just consider, so for this guy, you just consider a 1 point compactification of the whole R3 and turns into an S3 with 2 vertices there, and all the other guys just follow. So applying this Euler formula for the 1 point compactified R3 and the previous result, we find that the rank of the flavor symmetry is actually the number of semi-infinite cells minus 4, and this also matches the result from toric geometry. And I'll present some of the charge calculations here, which will be pretty quick. But here is also a choice, because now let's again consider this P1 times P1, a local P1 configuration, where you can just measure the charges here by first counting these Q charges. These are not really charges, they're defined to be 1/2 the number of 4 branes it ends on. So you get this configuration, and then you want to match it with the toric geometry, but this is actually up to a choice. It's not really, there's not really a canonical correspondence here. So you just make this choice. You can find, this different stringy states in AD give you the correct charge that you can compute from toric geometry. And this choice is also match the choice that has been made in the toric geometry in Yinan's talk. So here, some comments about the charges is that first, there's no canonical assignment of the charges, and you have to check it against your choice in the geometry. So that is a choice of the non-compact divisors in the toric geometry. But such a choice can always be made because this is about showing either a determined or underdetermined system, so a choice is generically possible here. So you can always try to match it with the toric geometry. So just several outlooks as the last page of my talk. So first, we have to think about whether we can see the flavor symmetry enhancements from the brane box. This is not yet touched in our work, and also I'm asked by several people that whether there's there's some GTP or generalized toric polygons, or in some literature called toric light diagram from the brane box. And I think the answer is yes, we can try to do that because we have the codimension 2 branes in AD as well. It's just that we haven't thought thoroughly about this problem, but this is a further direction that we can try to approach. And also there's, of course, the Higgs branch physics from brane box that is totally unknown for us. And also some math problems that whether we can construct a non-compact Calabi-Yau, like Ricci flat metric from this intersecting Tn configuration. So that concludes my talk. And thank you guys.
Questions?
Sorry, what?
Choose time slot from brane box.
Um,
Here we go.
No, we didn't compute that. Yeah, from brane box, because it's always dual to the toric geometry. So if you can compute it from toric geometry, that's fine. But I currently don't know how to do it from just purely the brane box level.
And you add the G4 flux, and right, you need to have a G4 flux.
Yeah, but
And
that's
then
not
the brane
known
box.
from the brane box picture. Yeah. Decouple what?
Chiral matter.
That's another problem because if you want chiral matter again, it's probably a problem of whether you can have G4 flux in the brane box. But again, it's not known because brane box is totally a dual to the geometry, and everything that is from flux is currently missed by the brane box construction.
Adding the D3 portion.
Yeah, I'm not sure. We can talk about it later. Yeah. Yeah. Please.
Can you go back to this conclusion page?
Yes.
Now that you mentioned this GPP,
Yes.
GPP, and also Higgsing. So I have just have a comment that when you do this Hanani to move, then it actually creates this non-toric like one, right?
Yes.
And that has also in 5 and 1, there's an interpretation as a Higgsing.
Yeah.
So probably this GTP and Higgs branches are probably related.
Yeah, I imagine so, but we haven't studied many Higgs branch physics and also like a full-fledged theory of Hanani-Witten moves in the brane box. So currently I don't know the answer, but that's a good comment.
Okay.
Yeah.
So
thanks.
another question is that when there's the planes are parallel to each other, do you also expect that there's some kind of enhancement because of the parallel planes?
Yes, of course. I mean, when you squeeze that, it's always, I mean, when they're parallel, you can always choose the strings between the parallel branes to be the W boson in that sector. So if you shrink that brane, of course, then you will see.
I'm talking about the flavors.
The flavors, yes, I think so. Because the flavors, I mean, when you have parallel, edges, you will try to just draw a string between those edges, and I do expect there are enhancements. But then also that then has to be checked against the geometry but we're lacking a good geometry where we can test intersection numbers in the geometry in the singular limit. So from brane box, yes, you can pretty much predict something. But then it's a problem of whether we can check it against other dual frames. So that's a problem. In the brane box, yes. Yes, you should be able to see the flavor symmetry enhancement from brane box. Yes.
Just the last question. You mentioned the monodromy. So here, monodromy matrix is a 3x3 or?
No. I say the monodromy here is again by decoupling some direction so that you are again back in the 5D case where the monodromy becomes Euro SL2Z monodromy of the 7 brane. Mm-hmm. And yes, there are this SL3Z transformation there, but I'm not sure whether it is probably called a monodromy or something. Maybe yes, but then it hints on the problem that how do you define a branch cut in R3, which is quite controversial. So I'm not sure. But anyway, you can try to you can imagine that there's an SL2Z embedding of SL3Z, and you can always check this SL2Z embedding, and that is a properly defined monodromy. Yes.
Any other questions? Toshi.
I'm very excited to see that so many things which we can do for fiber and web can be also done in this PQR setup. So, what we can do from fiber and web with one of the things is what I call like Simon-Witten curve. Did you consider any generalization of this Simon-Witten curve?
That's actually very interesting because there's an old paper from 2 decades ago by Merck about this about the 2A alkyl fourfold, where there are these toric constructions, and there they consider a generalization of Seiberg-Witten curve to be something like a Seiberg-Witten surface.
Oh.
So imagine now you have a Seiberg-Witten surface, and you can consider various puncture line or punctures on the surface, and you could try to think. But then the problem is that this is a mirror symmetry between 2A and 2A. So I'm not sure whether, because I'm not familiar with that, so I'm not sure whether there are, this serious quantum correction to that. But that I'm not sure. But there are actually, but not many works on that. Not many works. It's all from 90s, where they do consider some generalization of Seiberg-Witten curve to the surface case. And also in this case, I suspect whether there's a 3D correspondence that we're thinking about, because in 5D is nothing. The Seiberg-Witten curve is sort of the tropical geometry of the fibrate map. But here now, given a brane box, I'm not sure. This is just a wondering that whether there's some sort of a tropical geometry in real 3D, so that you can sort of make the brane box to be some real 3 manifold, so that you can study. Because anyways, the 3D correspondence gives you a 3D Su theory. So that should be also try to match the known construction. So that there are no literature on that aspect that I know of. But for the Columbia fourfold and sort of cyber-written surface, I mean, there are this, but not many literature. Probably just a 2 or 3 paper on that. Yeah.
Thank you.
By the way, is there any relation between the surface and some integral points?
Oh, that I don't know. That is beyond my scope. Sorry. Yeah. But I'd like to hear your answer. I mean, you're the expert, so I yeah, that is a very curious one. I
But
think.
the problem is that we don't really know what the gauge theory is.
Oh yeah, that's true. That's true. So you should just try to go to different dual frame and check against different realization of the same theory. Yeah.
Any other questions? If not, let's thank the speaker again. Okay, again the same. Hopefully students can help for students at the canteen.
Will we continue with this?
Oh yeah. So we will move. I think it's better to move the other room. I guess it's too wide and then not so much interaction here. What do you think? We can use. Okay, we can move. We can move over there.
Yeah, I can guess maybe.
Afternoon.
The seat is super soft.
Huh?
The seat is super soft.
Oh, do you feel better?
Yeah, it feels more better. Yeah.
Huh?
I enjoy this one.
Okay.
No, people get too rested in
Yeah.
the seats.
Yeah.
Too comfortable. I think
Yeah.
to listen to talks, academic talk or lecture, you need to be relatively uncomfortable.
Comfortable,
on your
okay.
seat, right?
Ah.
Okay.
Like the seat should be like full, just this